Hi, Elena.
Hi, Elena. Hello, Monsi.
Hi, Sada.
Hi, everyone.
Hello, everyone.
Yeah.
Hi, Nicholas.
Hi, everybody.
So I guess we can start in about 4 minutes to be compliant with the schedule.
Yeah, you can wait a little bit.
We can wait 4 minutes, yes.
This streaming is also live on YouTube. And okay, you can start recording too.
Mm-hmm.
Recording in progress.
Few more minutes. We're not, it's not that we're waiting for the speaker, it's just that we said that we would start at 12:05, so we're just waiting 1 more minute so that we can start on time, or the time that we set on the webpage, but yeah.
Hello. Who's speaking first this time?
Nicholas Hausegger.
Yeah. You should start, Elena.
Sorry?
You can start.
We can start? Okay, yeah, it's officially 5 minutes past 12. So, hi everyone, and welcome to the third session of this conference. And in this session, we're going to be talking about cosmology and the large-scale structure. And our invited speaker for this session is Nikolaus Sulzenauer from the Max Planck Institute of Astronomy in Bonn. And he's going to be talking about the correlated galaxy formation at the scale of the sun horizon. And what can protoclusters tell us about the distant cosmic web? So, Nikolaus, whenever you want to share your screen and start your presentation.
Yes, I'm ready. I can start. Okay, can you see my slides?
Yes, we can see them.
Okay. Okay, thank you very much. I want to start by, of course, thanking the organizers for this great event, great conference so far. Was really enjoying yesterday's talks. And yes, I would really like to pick up the discussion where we left it yesterday on a particular problem or challenge in modern cosmology regarding the largest scales, scales at the sound horizon, or even beyond that in the cosmic web. And I also want to mention that, especially in the early universe and at high redshift, we are still at a terra incognita phase of cosmography. However, there's a big promise in increasing our knowledge about how matter is distributed in the early universe, as this could give us valuable insights in the expansion history of the universe, of course, and to test if our models of structure formation really hold the test of empirical observations. And in this talk, I will bring radio astronomy for the rescue of some of these problems. But maybe we should not be too happy too early, because there might new problems might come up by doing that. And I will address these problems by looking at rare, highly star-forming so-called submillimeter galaxies. And to motivate this branch of science, of radio astronomy, I want to mention that it's important to understand that star formation is an ubiquitous phenomenon. It's universal. It really underlines the formation of galaxies. As we heard yesterday, there are galaxies now detected with the James Webb Space Telescope out to redshift 14, and there are a few candidates even beyond that. So it's really a fundamental process. And later on, especially in these early times, but also later on, galaxies merge. And it's believed that, or actually we see very good evidence for that, that galaxies build up hierarchically and towards larger and larger structures until we have a highly structured universe with a lot of different compartments, different phenomena that you observe, galaxy clusters, voids and filaments and all of these structures. But on the very smallest scales, on galaxies, we really have to look into star formation, into the process how galaxies really form their stars. And when I talk about extreme star-forming galaxies, it might be important to look at a few categories, how we could categorize them. So there are these four steps I want to introduce here, which are the first step would be a luminous infrared galaxy. That's a galaxy with about 10 times the star formation rate of our Milky Way. Then there are ultra-luminous infrared galaxies. That is yet again 10 times more brighter than a luminous infrared galaxy. So it would have 100 times the star formation rate of the Milky Way. And yet again, the hyperluminous and the extremely luminous are the next two steps, yet again, increasing by a factor of 10. And in my opinion, it's really remarkable that there's these objects that have 10,000 times the star formation rate of the Milky Way, if we really believe that. But of course, these objects are so rare that they can only be found in a huge volume and under very certain circumstances, very special circumstances. Especially, so what we need is really high gas densities and really violent galaxy interactions, and perhaps even additional heating mechanisms like black holes that can push star formation into a more exotic state. And up here you can see one of the benchmark objects, ARP 220. That's the most highly star-forming galaxy in the local universe, right at the edge of the local universe. And this would be a low luminosity ULIRC, at the lower end of ULIRC. So there are galaxies that are 10 times, forming 10 times more stars than that. And all of this really fits into this time series that I already tried to outline. A time series that starts at very high redshifts, where tiny galaxies merge to larger structures. And in between, we have phases where supermassive black holes might heat the gas, really expel a lot of the cold gas and shut down the star formation, and you're left with quenched, quiescent early type galaxies, for instance. That's a very common picture. And there's very good evidence that we also see this kind of evolution in the universe. And in the very end, after going through these extreme phases of high Lyric and extremely luminous galaxy, infrared galaxy, these objects would really evolve into the cores of local galaxy clusters. Because if you have an episode of 5,000 solar masses per year star formation event, you can imagine that you can form a Milky Way-sized galaxy very, very quickly. So you can really form these enormous, very heavy, very massive early types very quickly and in the high redshift already. This is what one of these objects looks like. We have my team has imaged that with ALMA in spectral lines. This is what you can see here in this animation, is a position velocity diagram in 3D of two massive galaxies that are interacting with each other, just a few tens of kiloparsecs apart from each other, and hosting star formation event of 3,000 solar masses per year. And now it's known to have at least 1 or 2 dozens more dwarf galaxies that are in the halo around this massive merger. So we really believe that this object will evolve into a galaxy cluster. I forgot to mention we observed this at a redshift 6.9. So that's about 800 mega years after the Big Bang. Before I come to the main point of my talk, I want to introduce 2 aspects that are really important to understand why these kind of galaxies are so interesting to me. First of all, why can we actually observe these galaxies when they're so far away, and there's cosmic expansion in between and other things that might really complicate, that typically complicate, for instance, in the optical, the identification of these objects. And it all boils down to the so-called negative K correction. So this means at certain frequencies or wavelengths, it is possible to look at this kind of galaxy or to identify this kind of galaxy population at any redshift between 2 and 10. They don't decrease in brightness, but actually become brighter until redshift of 10. Then they really drop out very, very quickly, and it's very, very difficult to see them. Also because this only is valid for a monolithic population, so no evolution in the population properties, which we of course do not expect. We expect some kind of cosmic evolution with galaxies. So we can observe them, and we can efficiently observe them at high redshift. That's the first point. And the second point is that it has been known for a long time now, for more than 20 years, from the 2-point correlation function of the submillimeter galaxies. Here, as a sketch, the red dots would be the submillimeter galaxies, that they have, that the autocorrelation of these galaxies is found to be about 7 proper megaparsecs per each. And this would mean that when we factor in cosmic expansion, that we expect to find the descendants of these objects really in the cores of galaxy clusters. This is what this figure shows down here. So typically we see the submillimeter galaxies at redshift 2, 3, and above. And when we dial forward cosmic evolution, these galaxies are expected to grow into centers of clusters, as shown here. And another way of looking at this is to look at the masses, the dynamical masses of these galaxies. So looking at the halo where these galaxies might be embedded, whatever this halo constitutes, but these galaxies have a mass, and we expect only certain certain masses of halos to be associated with, for instance, molecular gas masses of 10 to the 11 solar masses that I just mentioned before. So these very, very massive, very, very large molecular gas reservoirs also need very massive halos to host host this baryonic mass content. And for this reason, submillimeter galaxies, especially high lurks, so the very bright end, the very luminous end, should be an excellent tracer for the formation of the cosmic web. So for the formation of galaxy clusters and for the structure in the universe. And over the past years, since these first studies came out, there has been a lot of initiatives to look for protoclusters. This means groups of galaxies that at redshift 0 should evolve into a bound virialized structure with a hot X-ray atmosphere and other effects that are very typical to clusters, like the mass or the richness in galaxies. What people found is that there's a large variety of protoclusters. We'll show this a bit later. But for now, it's really important to understand that the giant elliptical galaxies, again, that we see in the cores of the clusters, as very nicely illustrated in this figure here, like here, these very giant elliptical galaxies, these are really the descendants of these enormous starburst events. However, still, you see this autocorrelation, but it's really hard to tell by looking at the redshifted submillimeter galaxy at redshift 5. It's really hard to tell, even if it's an enormous gas reservoir, if this galaxy will evolve into a center of a cluster, will actually evolve into this object. This is due to the highly nonlinear fashion at these scales, at few megaparsec scales, where you cannot really apply linear evolution in any sense, but you really have to look at how the configuration of subhalos is, how their neighborhood looks like, how the neighboring large-scale structure is constituted, in order to figure out if if this galaxy will evolve into a galaxy cluster. So really, the environment is crucial to learn more about that. And there's also other good evidence. Here, yesterday we already talked. Sebastian, I think he showed us already from the DAISY collaboration the measurements of the baryonic acoustic oscillation. So the power spectrum in the two-point correlation of galaxies at different redshifts. This is what's shown here. And what we find is, when we compare that, that there is a quite constant peak in the two-point correlation function at or power spectrum at about 150 co-moving megaparsecs. And this peak can be traced back to the 1 degree peak in the CMB fluctuations. And on one hand, so at redshift 1100, and at redshift 0, there was a really intriguing paper from last year where they were able to identify one of these bubbles, of this 150 megaparsec sized bubbles in the very cosmic neighborhood surrounding the Boötes supercluster. So these are the black points in here, and surrounding this supercluster is a complex of many other clusters that form this giant bubble of diameter of 150 megaparsecs that is interpreted as a BAO, as a baryonic acoustic oscillation relic from very early times. So that's the other evidence, and that's the other side of it, large-scale structure formation. And now the question is, can we see this at high redshift? Can we see this already in massive or highly starbursting submillimeter galaxies? Because then we could really figure out if they are forming a cluster or not. And for this reason, I want to introduce the object called HS 1549. This protocluster was initially identified by following up fields around bright, luminous quasars. So this quasar at the time of discovery was the most luminous known. And And later follow-up campaigns with large-scale imaging and narrow filters are targeting the Lyman alpha emission around this hyperluminous QSO, found that there's a really highly extended, so here you have the scale 120 cubic megaparsecs extended structure in Lyman alpha emitters. This means Lyman alpha emitters are normal star-forming galaxies typically. So they're not very dusty, they don't have as much ISM, but they still are quite star-forming and can be found everywhere in the Redshift universe. However, it's rare to see them structured in such a way to really trace large-scale structure over 120 cubic megaparsecs. And this is a very good sign for a protocluster information. Over the next decade, people also looked into the submillimeter in order to find massive galaxies information. And what they found is that surrounding this hyperluminous QSO are a large number of really bright submillimeter galaxies. Cannot be seen too well in this image here from the original paper, but these black dots are all really bright hyperluminous infrared galaxies. So there's actually a top-heavy, one could say, a top-heavy luminosity function that surrounds this QSO in the center in this field, with more than 15 hyperluminous infrared galaxies or massive submillimeter galaxies. Because the problem is, if we do imaging, we cannot really infer the distances. So it could still be, at this point in the year 2019, it was not clear if it is a projection, like galaxies that are in the foreground just projected to it, or if this is really a 3D structure at the same distance. You can also see on the right-hand side a zoom in to the very center region. This guy here is the QSO, and these are nearby massive galaxies. And you can also see the green contours are the submillimeter emission. The background is IRAC Spitzer, so near infrared stellar light, redshift 2.8. Okay, next step, and this is when things took a turn. My team did follow up again of these submillimeter observations, targeting the individual bright submillimeter galaxies that they found with spectral scans. So with spectral scans, it's really possible to tell the distance and to tell the 3D structure. And by doing that, we were really able to find that 15 hyperluminous infrared galaxies are contained in this very large structure that was already known from the Lyman alpha emitters. So this is what's shown here on the left side in contours are the number density of Lyman alpha emitters. So it's this bar-like structure almost, like a bar. Here, the very center around the QSO, and the stars, the white stars, are the hyperluminous infrared galaxies that we are now able to identify based on their molecular gas emission. And there's another about 10 candidates that we work on right now, also within this large-scale structure around it. The size of this structure, since we did not target the entire area that I showed before, but only the central part, we cannot really tell how large it really is. But from what we targeted so far, we found that it's really 20 by 30 proper megaparsecs extended in massive galaxies information in this high lurks. And it's also about 10 megaparsecs deep. So it's you could imagine it as maybe cigar shape or even pancake shape. And this is what George Wang, a PhD student at the University of British Columbia, who led this study, what he found is that these submillimeter galaxies are arranged in a pancake-like structure, something that looks a lot like a sheet of the cosmic web that is collapsing. And furthermore, he found that we are really looking at more than 20,000 solar masses per year of star formation in total, if we sum up all the contribution from the massive star-forming galaxies. And this does not even include the Lyman alpha emitters. There are more than 100 Lyman alpha emitters that also would contribute to this star formation rate, of course. And this means that this is easily the record holder for the highest star-forming connected structure, 3D structure that we know so far, of which we have good measurements. And as I said, the massive galaxies really seem to be connected in this bar of less massive star-forming galaxies. So it's really a hierarchy of different galaxy types forming stars. I already mentioned the pancake. This is really a remarkable finding that when you look, if you could rotate around the universe and look from a different angle on the structure, we believe that it would pretty much form a roundish structure with maybe one or two outliers. That's not so clear. So these data points here again are the submillimeter galaxies. This is more or less the same view as I've shown before, face on as we see it on the sky. And from the other direction, it would be relatively flat. But overall, it's a very good indication of a coherent single structure. Also from the redshift distribution, there's a very strong peak that is extremely well aligned with the Lyman alpha emitters in gray. So this really works out. However, when we look into the details of the velocity structure, this is what's shown here, a phase-space plot that is quite common for when we study galaxy clusters, virialized structures. We can define a mass, point mass or standard mass, and look what would be the escape velocity that a galaxy would need to be no longer bound to the structure. And that's drawn in here by the gray and black contours. And just as a rough estimate, because you can probably imagine it's quite difficult if you don't know the details of the shape of this object. It's hard to assume more complicated models. But if you assume a point mass as a first order approximation, we would actually need at least 10 to the power of, or 3 times 10 to the power of 15 solar masses to keep this structure bound. Maybe even more, because there are a lot of submillimeter galaxies in blue that are even beyond that, and very few actually that are within it. And it's hard to understand why that is and how this really works together. But when we look beyond the very core, where you have the QSO and where it seems to be somewhat quasi-virialized, so beyond 2 proper megaparsecs, there is this really large velocity offset. And the masses would be too high to really, at this redshift, at redshift 2.8, at 3 times 10 to the 15 solar masses is not expected in any way. So it's not really clear what this means. So it would be better to look at a different estimate for the masses that we expect to be contained. But this also proved difficult because even the very largest and best suited cosmological simulation, embodied simulations that are currently available are not able to reproduce the halo masses that we see around the structure. So what we did for this analysis is to select a central halo mass of 10 to the power of 14 solar masses. This is what we expect for the QSO and the very center part, where a lot of Lyman alpha emitters very well trace the kinematics, and we can actually infer the dynamical mass. So this is about right. And then we select such masses from this large-scale simulation and ask the question, what is the median mass of the 10th of the 10th most massive halo nearby. That's what's shown here. So we select this central halo and then ask what are the satellite masses, the median satellite masses. And what we found from this simulation is that no single, so this the 10th most massive galaxy is already a factor of 2 less massive than what we expect for Hilux at all. So it is not really possible, or at least with this simulation and this configuration, we cannot find we cannot find a structure that is similar to HS 1549, because we would not expect to see as a 10th most massive neighbor any halo that could host actually such a cold gas reservoir as we see. But this really begs the question: what is this object, and also how rare it is? How rare is it? And at the moment, numerical simulations cannot really help us. At the same time, there is a conflicting problem that is really a long-standing conundrum in massive galaxy formation, connected to Hilux and submillimeter galaxies. And this is, why do we see these correlated starbursts among a few megaparsecs in distance? So why are these halos starbursting at the same time, even if they don't really have time to interact with each other, for instance? And there are two, we see this quite often, that's quite common, as we also see it in HS 1549, because you can imagine if you have star formation rates 1,000 solar masses per year and a molecular gas reservoir of 10 to the 11, you can maybe sustain it for a few tens of mega years, but not longer than that. And just by chance to see 10 of these objects at the same time is rare and it's unexpected. So there are two solutions to this conundrum that were proposed in this really nice little paper. First of all, if the gas depletion times are longer, then of course the odds of observing such a correlated large-scale star formation event, about tens of different halos, also increases. And then it's just a number game of observing a large enough volume to find such correlated structures by chance. However, there's a second solution to that is, in my opinion, more interesting and might actually help us in understanding what HS 1549 really is. And this is connected to the larger scale, so the larger environment around this protocluster. On the IGM scale and really in the cosmic web where it's forming. I will go more into that in a moment, but before that, I want to show a few other observations from the literature to give you an idea how rare it really is, what we found here. First of all, it's also important to mention that HS 1549, the one I just showed you, is part of a sample of 2 objects. The other object is HS 1700, which was also selected around a QSO and with a lot of Lyman break galaxies around it. So it is expected also to host a protocluster-like structure. And it's a bit early, but we have the first data coming in, and it seems like that this is also a similar object, although not as star-forming, not as extremely star-forming. It's also slightly lower redshifts, so it's redshift 2.3. Blue and red are these two here, but it's clear that these two objects really trace out accelerated structure formation at high redshift. So for these objects, it's safe to say that submillimeter galaxies trace the large-scale structure. What about other objects, more well-known ones? Here's a small compilation of these protoclusters that contain Hilux and highly star-forming galaxies. These highly star-forming galaxies, the submillimeter galaxies, are shown as colored dots. At the very lowest end, the luminous infrared galaxy end, so to say, would be here in blue, and the very highest ones are the yellow ones. And down here you can see HS 1549, and you can tell there's really no other structure that is the same size. So the next one is SSA22, which is very well known and shares a lot of similar properties to HS1549, but it's maybe a factor of 2 to 3 smaller. To really get this entire coherent structure as in HS1549, it's not the same size, and it's not the same kind of object. And the other ones that we know of are much smaller. Especially one of the first samples of first targeted statistical samples that we have of protoclusters containing submillimeter galaxies turned out to be all protocluster cores. So that's even smaller than the typical protoclusters that we see. So these would really only form the very central BCG, the very central massive galaxy. None of the other satellite galaxies, really a collapse event of the central galaxy. And this is what's shown here as a zoom in. You can see this blended overdensities, and then another zoom in with ALMA, high resolution imaging of these structures. And yet another zoom in, going in a factor of 100 compared to the original one. Here we see these cores, the very cores, they're just a single massive galaxies forming in a very rapid event, but they also contain a lot of these highlights. There are 3 highlights in the structure as well, but on a factor of 100 smaller scales than HS1549. So just to mention it, in terms of highly star-forming galaxies, HS1549 is very special, as it is much more extended. It seems to host a lot of correlated, but still individual halos or density peaks that form stars, form galaxies. One of the community favorites that's also known for many years now is Hyperion in the Cosmos field. As far as I know, this does not contain any submillimeter galaxies. But it's also large. It's similar in size. So it also has this 150 co-moving megaparsec. So really at the scale, the co-moving scale, acoustic scale of the universe. And if we believe this number, it is about this like 5 times 10 to the 15 solar masses. But I'm not really convinced about that. And what's really interesting is if you look at this pencil beam survey. So again, this is when taking a small survey on the sky and just flipping it and looking how the galaxies are along the line of sight, where they are distributed along the line of sight. We see that there's really this periodic pattern of 150 co-moving megaparsecs between these density peaks traced out by Lyman alpha emitters. And this is what we quite frequently see in these surveys. For protoclusters, then we are only really interested in the highest density peaks, like this new one here, and the Hyperion is composed of these 2 substructures. More recently is the Elantari proto supercluster. So now the community became courageous, and now they really call these structures superclusters or proto superclusters. Because it's really not sure if they will ever viralize into a single cluster-like halo with many satellites, but a single structure. Because they're so large on the sky and also in velocity, that it's more likely that they will stay separate, evolve separately, and over time have cluster mergers within them, but probably still have multiple components that are separated. And for this one, they did a very nice study where they looked at how a linear evolution of linear spherical collapse model, what the predictions are of merging of the individual clumps that they found here, like these 6 density peaks that are separated by 70 co-moving megaparsecs, and also show quite a broad redshift separation or velocity separation along the line of sight. And again, we are talking about cluster masses of the individual. So these are really for the individual halos, which are really, which is likely that they viralize at one point into coma-like structures. this one, the Terrelay proto-supercluster, is the highest redshift of the supercluster objects at 4.5. So that's about 1.5 gigayears after the Big Bang. So these objects form quite early, and it's really interesting and really intriguing to see how quickly the cosmic web forms and how quickly it collapses into galaxies and into individual structures within it. But again, same as with Hyperion and with Elantari, this one does not contain any bright submillimeter galaxies as far as I know. These are normal galaxies, Lyman alpha emitters. And but again, these are proto-superclusters that all should evolve into at least coma type objects by redshift 0. I also want to bring up this really intriguing new findings. I'm not 100% sure if it really fits into this family portrait of proto-superclusters. However, it's super intriguing. It's the big ring on the sky, where they claimed that they found a 400 cubic megaparsec diameter ring that would be about 5 degrees on the sky, actually. So really, really large, on the same scale as some constellations, at a bit lower redshift, 0.8. So not really high redshift, but of course, still it's halfway across the universe. There's a lot of time still to form clusters within. And they found this by looking at magnesium-2 absorbers. So it's not the galaxies that emit light, but it's by background sources that contain traces of foreground structures. And it's this foreground structure that seemed to follow this or fall into this ring-like, huge, large-scale structure. Yeah, so I'm not really sure how this fits into that, but certainly an intriguing finding. Okay, so now in the very end, I want to talk about some interpretations and how we can make sense of these proto-super clusters, and especially HS 1549. And for this, I think it's advised to look at the Seldovich approximation for cosmic web formation, which is a formulation that helps to calculate properties of the cosmic web by looking at a two-dimensional sheet where the density structures undergo shell crossing and caustics form. And within this caustics, structure is formed, galaxies are formed. And what's interesting about that is that these shell crossings cause shocks in the gas. So of course, at high redshift, we still expect most of the baryons to be in gas form, and there's still, most galaxies are still to be found. So if you have large-scale shocks on megaparsecs in the gas, you would also expect to, of course, you push up the density, and this might really push galaxy formation within megaparsec scales. That's the idea. So here it's just very nice to look at it. I mean, this is a phenomenological similarity, but it's still really nice to just compare by eye how caustics from a wavy field, whatever this field is, compares to large-scale simulations of structures and filaments and voids between them. But of course, we would need much more data to really show that these shell crossings that push up the local densities across filaments and across sheets, if this can foster galaxy formation within them. But I think this would be a good way forward to explore this idea, especially because there is evidence for a modified state of the gas inside protoclusters that are not governed by the galaxies, but seem to really come from a larger scale structure. And here I want to show Lyman alpha emission again, but now it's not point sources, but it's diffuse Lyman alpha emission. So this is gas that has been ionized and now radiates Lyman alpha photons on large scales. So here, this structure shown here is over 1 megaparsec in length, and it's part of ESO-VLT Muse observations. This means the field of view is relatively small. I don't remember at the top of my head how large it is, but it could. What I want to say is that this could be a much larger structure, and we know that in SSA22, the protocluster where this was observed, we have very large scale diffuse Lyman alpha emission. And I think it's very intriguing comparing this to shell crossing events, especially when looking at the velocity difference of these linear thin structures that are separated in velocity by quite a large amount. So here you have plus minus about 1,000 kilometers per second within a relatively small area, or a relatively small distance from each other, what I wanted to say. And this might be quite interesting to explore further. There are also challenges coming from another side. So now we talked about what could solve the conundrum of correlated galaxy formation, massive galaxy formation. But then there's another problem on the small scales, on the ISM of star-forming galaxies, highly star-forming galaxies. And the problem is that at the moment, it's actually not possible to reproduce hyperluminous infrared galaxies in the laboratory. I mean, of course, in numerical simulations. We don't have the recipes to really reproduce the properties of the cold gas, of the enormous cold gas and dust properties that coexist with this enormous star formation rates at the same time. We don't have it at the moment. It's a multi-scale problem. And in my opinion, it's also related because it does not include all of the environment. So as we've seen, there are these large-scale gaseous structures on megaparsecs outside of the galaxies. And it's really possible that we have the merger, very short time duration, but at the same time, the galaxy also accretes gas from the outside, accretes dwarf galaxies almost constantly. This is what is expected from some of the simulations, and all of these effects taken together, all the shocks, all the small scale physics, it's really hard to reproduce this in simulations, and that's really the problem. So it might be that HS1549 is not only interesting from large scale structure point of view, but also from the small scale ISM point of view, because both have to work together to explain the distribution of these hyperluminous infrared galaxies on the sky, on the acoustic scale, and secondly, they also have to reproduce the galaxies themselves, the galaxy properties themselves, as hyperluminous galaxies. So I think looking for more pancakes in the early universe might really inform future galaxy formation and really could help to ease some of these challenges that we face right now. And maybe something I haven't talked too much about is it a challenge to lambda CDM at all? So this is really unclear because we have these two other problems that we would have to solve first. On the large scale structure and then on the galaxy scale. But for sure, HS1549 would be a great benchmark. And regarding the other examples that I showed, the galaxy protoclusters that contain normal star-forming galaxies on large scales, they don't really seem to be a problem with lambda CDM so far. Yeah. Structures that contain submillimeter galaxies might be. And yeah, with that, I just want to close that having more of these objects, a larger sample, might also help us to learn more about the Hubble function, the galaxy or structure formation early on, and maybe even about sigma 8 as we trace the highest mass group environments on megaparsec scales. But this, of course, would require hundreds of objects in our sample, which we don't have so far. Okay, that's it. I'm happy to take any questions.
Well, thanks a lot, Nicholas, for the super great talk. And yeah, if anyone has any questions. Okay, so Pavel, if you want to go first.
Okay, yeah, thank you. So this was really an exciting and wonderful overview of this topic. Much of it also new for me. And so thank you, although you're next door, right? So one should really talk much more. And if I may just put up a word of warning, on your slide 3, you showed the sequence of galaxies with, I don't know if you could show it just to remind people. Exactly at the lower end, you see you're showing a major gas-rich merger, right? And then like this is being, and you also argue that this is evidence for this merging build-up of structures. And I'd just like to warn you there that when you see these on the lower left, these two galaxies, what we see is two galaxies interaction, and whether they merge is an interpretation, right? And they will only merge quickly if they have dark matter halos. Otherwise, they are just flying past each other, interacting, and then they would probably merge on a much longer time scale. And so I'm just warning that please, also for the benefit of the younger astronomers who constantly hear this and see these images, and they somehow magically associate this idea that whenever galaxies are interacting, they are called mergers, that this is an overinterpretation of the data. So please, this is just I'm trying to get the astronomical community here more up to scratch, in particular since the direct tests for the existence of dark matter actually exclude its existence. I mean, this is what I talked about yesterday, and one can't ignore that evidence just because the whole community continues saying that this is a merger, which it probably is not. It's an interaction. And have you tried to connect? I mean, you've wonderfully shown how the structures you're seeing are in tension with lambda CDM in the sense of that particular theory having difficulty producing these really massive structures which you are finding. Have you tried to connect that with the El Gordo cluster, where Elena has done quite a lot of work? Because El Gordo is at a lower redshift, I agree, but it's still a fairly high redshift, too high redshift, and that galaxy cluster can't actually be understood in terms of lambda CDM. And so that cluster at a redshift of something like 2 or 3 might look similar to what you're looking at, perhaps? I don't know.
I think so. It could. So I haven't looked into it, but this should be done. It's really interesting, actually, to look at the velocity, right? This was one of the findings, that the collision velocities would be too high. Yes, so I think it would imply that, because if you have these subpeaks that are at redshift 2.8 that already have coma masses and are only a few megaparsecs from each other, this might imply that there's very quick evolution, very high dynamical interactions. But yeah, I haven't looked into it yet. I wanted to include a slide initially, but then, yeah, sorry for that. I did not include it in the end. But would be really nice to look at objects at redshift 1 to see how they evolve, really.
Yeah, thanks.
Are there any more questions regarding the talk?
Elena, you are mute.
Oh,
Sorry, I did not notice. No, I was just asking if there are any more questions for Nicholas' talk. If no one else has more questions.
Maybe I can ask another one.
Yeah, of course.
Concerning the IMF, which was actually also mentioned, and you mentioned it, right? So there is a formalism with which you can apply. So when you see these systems and you calculate the star formation rate given standard methods, one could in principle recalculate the star formation rates assuming the IGMF theory, just to see what sort of estimate that gives. And there the star formation rates would be lower, and they implied masses of the systems also. So maybe that would be an interesting a study to do, because the framework exists. The IGMF theory allows one to do these type of calculations. So that's just basically a comment. So
yeah, yeah, very interesting. I agree. Yes, yes, yes. And we have other evidence from the cold gas. Actually, this is emerging science that the IMF is really, really different in these ones. Top heavy.
Okay, so if there are no more questions, we can thank again our speaker. Thank you again for the very nice talk.
Actually, may I
Sorry.
ask a very quick question?
Of course, yeah.
Yeah. Actually, I was just wondering, most of the focus has been in these studies using the lambda CDM models, and but there are alternative models. They don't have the kind of, means they have not got such a limelight that they are considered for these kind of studies. So I think one of the reasons we find that the lambda CDM model is so successful is because so much resources are put in there to show that it is a good model. Whereas other budding models, including MOND or something, which Pavel has been talking about, and others, they have very limited resources to put in there. Even the models have not been developed to the extent to really prove or disprove them. So I just want to have this comment, and maybe Nicholas can say something about it.
Yeah, thank you for this comment. I'm not sure if I'm the best qualified person, because I don't directly work on models that much. But I fully agree with you, of course. I mean, it has been the standard model, right? A lambda CDM. So most resources are in there. And I see it the same way. But sorry, I cannot really comment it too much. I'm sure in the audience there are others who might say more about it.
So
Thank you.
if Indranil wants to say something also about this or about the talk.
No, I don't have a question, like a comment on that particular point. So I guess in general, it's true that sometimes you find problems with the model, and without the resources to show that they can be solved, that's simply not demonstrated. People stuck thinking that's the problem. But no, I don't want to comment on that. What I want to comment on is the slides you were showing regarding the very low redshift baryon acoustic oscillation feature, the so-called Huleilana, that was claimed at redshift 0.07. That's actually really interesting. I was actually looking at that study by Tully, I think, and Pomerade and others, and they actually find with mocks that, yeah, indeed, it's quite plausible that was a real BAO feature. There's only like a % or lower like false detection probability. So if that is a real BAO feature, which seems very likely, then one can of course use it to do cosmology by looking at the distance and the angular size of the feature, and also the redshift depth of the feature. And if you do that, then you actually end up with high estimate for the Hubble constant, or effectively there's a slight deviation from the Planck cosmology, and that actually is very much in line with the void model, because the distance to that redshift is 10% lower than in the Planck cosmology, if you assume the Planck cosmology is correct at high redshift and gets the right sound horizon. So yeah, that's actually a really interesting thing. It gives you like an additional BAO point at very low redshift of 0.07. So that's what, just a comment. I guess people should look that up online, the Huleilana, if they want to learn more about it.
Okay, so thank you very much for the comment, and I guess we should move now to the contributed talks, which are 15 plus 5 minutes. So the first of our contributed talk speakers is Rajendra Gupta from the University of Ottawa. And the title of his talk is Are Dark Matter and Dark Energy Manifestations of Covariant Coupling Constants? So whenever you want, Rajendra, you can start sharing and
Sure. Okay. Thank you very much, Arna. Yeah, I'm going to talk about the subject of whether the covariant coupling constants can represent the dark matter and dark energy in some form. So I think this is originally started based on the James Webb observations with excessively large number of galaxies at very high redshift, say that over 10 to 15, universe age only about 0.5 to 0.3 gigayears according to the ΛCDM model, which is not foreseen by the standard cosmological model. Galaxies at these redshifts have disks and bulges, which indicate that they have passed through a long period of evolution, and spectroscopically these galaxies resemble their counterparts in the local universe, and smaller galaxies appear to be more massive than larger ones, which is quite the opposite of the common view. Let's see why it did not moving. Okay, yes. So some of the thing is, you might say, in the impossible early galaxy syndrome, like the Macy galaxy is one of that. Macy galaxy is the one which is at very high redshift at 390 million years after the Big Bang. Other one is this glass Z12 or Z12 galaxy, which is even earlier, 350 million years after the Big Bang. Then impossible early galaxy, which you might say JSZ14. This is the highest Z galaxy, redshift galaxy, which is again at 290 million years after the Big Bang. Another one is this galaxy, which is Ribble 25, which is so well formed, just looks like our own galaxy, with the disks well formed, which is at 700 million years after the Big Bang. And some of the other problems are like this is also not very well understood, is a sampling of red dots, which have been spotted in early universe. And if we just recently, I came across an article which had this very nice graphic representation, which says unexpectedly bright galaxies, mysterious little red dots, these bright galaxies, and then surprisingly massive black holes and galaxies shaped like pickles or grapes have been spotted all over the universe. So these are the things which essentially lead us to think is the current, and they are not easily explained by the existing models. So one has to think whether there are alternatives. So I came across a paper 2 years ago, almost 2 years ago, which was trying to explain the James Webb observation of angular diameter of the observed galaxies. In different models, these angular diameters of the observed sources are different. So when we say it's extremely small, that is according to ΛCDM model. If you go to some other thing like this person really in this paper, Langevin, Lovick-Eggen, he showed that if you use the tired light, then tired light theory, of course, is not accepted in any general way, but it does reproduce the results, angular sizes of these, and it gives the, if you see the 10 kiloparsec size object as expected to be seen in different redshifts, then you get this kind of graph. That means you have an order of magnitude increase in the size when you go from the ΛCDM model to the twilight model, which is really, that means these objects are not so compact as were thought. So that led us to think, but twilight model is not really consistent with a lot of other data like supernova data. Eric Lerner would perhaps disagree with that, but with due respect, I could say that this thing doesn't really fit that data. It is fails the Tolman brightness test, CMB observation fails time dilation, all these things. So as a result, that is TL model, twilight model is not really satisfactory. Then we say, okay, how about if we combine the twilight model with ΛCDM model? Can it explain some things? And I will show in the next slide that it doesn't do that, although twilight model does fit the supernova data when combined with ΛCDM. And of course, ΛCDM on its own does fit the data very well. Then there's another one which I was studying, a covariant coupling constant model for some time. Then I combined it with twilight, and we find it gets a very good fit. And also it gives the very good fit with the James Webb data and complies with the Bow baryon acoustic oscillation, sound horizon measurement. But problem, it increases the age of the universe. That was a major concern at that point. So let's see what happens when we try to fit these various models with the observed data from before the James Webb. These are in the blue, and the James Webb are in the red. When we try to fit that thing, then we find that if we just use the ΛCDM model, this data doesn't fit well. We use the covariant coupling constant model, which I will discuss in a moment in more detail. It doesn't fit well. ΛCDM plus twilight, it doesn't do well. But covariant coupling constant plus twilight, it's pretty good. And then twilight, of course, is good anyway. So let's try to go to what is the covariant coupling constant model. Covariant coupling constant model is based on variation of all coupling constant can be represented by one dimensionless function based on local energy conservation. I don't have time to go into detail, but essentially if we take the functional form could be any, but I have assumed this kind of functional form, which is alpha is a constant in this. That means we can write the correlation between that using a single function in this form. That means all these functions, C, G, H, Planck constant, Boltzmann constant, they have this relationship. If we look deeper into that, then we find that dimensionally, if we see that if we focus on the length dimension, all these, then we can say this length dimension is the one which is determining the exponent of the function f in here. So, and how it varies when we try to fit the data and calculate the alpha, this is the kind of variation we get in these constants. And one thing we have to consider, if we constrain one of these, then we have to constrain all these, because it is the function f which is really we have to determine when we are trying to see measure the variation of a constant, not of an individual constant. Now, if we see the angular diameter distance in different models, they definitely have different shapes. They peak at different level. Of course, starlight will not. It will continuously going up. There's no peak in there. But all of them, we give different angular diameter distance. When we can calculate the age of the universe for these, then we get this kind of curves. That means we are getting age of the universe in the CCC plus TL model, we are getting 26.7 gigayears. Lambda CDM plus starlight, we are getting 19.3 gigayears in here. And of course, lambda CDM and CCC, they have very close to 13.8 gigayear, which is our normal. Now we want to see what is the age ratio at different redshift in the CCC plus TL by lambda CDM. You would say compare it to the lambda CDM measure. Essentially, how much is the age increase happens? So at greater than 10, it is greater than 10 as Z equal to 10 here, and is greater than 40 in if you go to 100, and even more later on, where it's in lambda CDM, this thing is age increases are not that significant at different times. So we have, even if at 10, we have an order of magnitude more time available for the formation of galaxies when we are using this model. So it's not the age increase which is at current value, but at earlier time, there was more time available for the formation of galaxies. Now, what is the contribution? What is the contribution of the redshift in the expanding model, expanding component in the twilight, which we find is also very shown in the variation in this curve, which can be quite significant in the case of the CCC plus GL model. It can be 3.5%, for example, at Z equal to 1,000, 22% at. So there is a significant contribution at current time, but earlier time there is not so much. And lambda CDM model, of course, at early time it's very, very much less. Okay, so let's see. This is the size of the. So this graph shows how is the increase in the size, which is at different Z. The size of the object increase is shown in this graph. I won't go in much detail in that one. Let's try to see what this model is, because this is our main objective is this. If we allow the speed of light to vary, and the measurement using the speed of light, the FLRW matrix is modified and becomes this, essentially. So we have ft squared here, ft squared here. Then Einstein equations become h plus alpha squared equal to this. And the second, I would say the Friedmann equation become like this. And the continuity equation. Now, what we can do, how we do the fitting of the curves is by using, we can say what is the proper distance. We calculate this proper distance in the twilight, compare these two distances traveled are the same. So by comparing them and using this relation, we find from very small redshift limit, we find the relationship between HT and HX, how they are combined, and solving with this equation, we can find ZX in terms of ZL and hence also ZT. After we account for energy loss due to redshift and time dilation, our distance model can be written in this form, which is fairly standard. Okay. So this is for fitting the supernova data, for example. Now, what happens, why we see this is manifestation of a manifestation of the dark matter and dark energy. So we can write H square in this form. From previous one, you remember H plus alpha square, H plus alpha whole square equals 8 pi G over 3c square. So in the flat universe, we have removed that K component, the curvature component. So this becomes like this, and we have this equation. So eventually, by massaging this equation, we get this kind of relationship here. So essentially, what we have is for the CCC plus TL model, what we are getting is that alpha, what we get is this is the first component, which is the baryon. This is the second one. The dark energy can be considered this one, alpha involved in here, and this is the product of the first and second, the square root taken times twice, like this. So this means the alpha represents really the dark matter and dark energy in this. Then, similar to Verlinde's emergent gravity concept, where he has shown that the dark matter can be represented as a product of the dark energy and baryon square root of that, essentially. So this is why I say that these things are dark energy and dark energy are. Now, I'm not going to go into detail because of the time component that the model fits the bow baryon acoustic data well. I've shown in this one, which is the absolute scale of bow estimated at low redshift in thin bins from measured angular galaxy distribution power spectrum using the CCC plus TL and lambda CDM plus TL model. This is our lambda CDM model, and we find that it gives this 151 megaparsec, the acoustic scale in this. Lambda CDM is about the same within the margin of error. They are not very different. Sound horizon, if we take sound horizon to be 0.60 degrees as Planck data, then we get 100% of the matter density comes through the critical density, which is only 3.1% of the lambda CDM value. No need for dark matter in the CCC plus TL model or dark energy. The star formation rate, and if you see the gene density is modified as a result, star formation can become earlier, and that's another advantage of this. So I think I might be running out of time, so I'm not going to go into. You can design experiments in which coupling constant variation do not cancel. This is very difficult. This is one problem which happens when you try to measure the testing of G or C variation. Then Kepler third law, when you use that, then we have this R cube and G, they cancel out in terms of F variation, covariant coupling constant. Gravitational lensing, same thing happens, G and C cube cancel out. Gravitational waves, so we can't find any experiment which can really measure the variation of G, C, or any of these because of the cancellation effect. So these are some of the criticisms of this approach. More fit parameters than the lambda CDM model? No, there are two parameters for both models. Time dilation observed in supernova 1A not included? No. So essentially, I have tried to explain that all these objections which we have, they are not really valid. In summary, I can say CCC-TL model resolves impossible early galaxy problem consistent with CMB, first peak, and bow data, yields baryon density about the same as lambda CDM model, but without the dark matter, constant variation prediction not in conflict with observations star formation can begin at higher redshift. So this is immediate future work is CMB power spectrum, which we are working on, BBN abundance, globular cluster ages, galaxy formation, LSS. And I should mention we are seeking collaboration. We do have some financial support for this kind of work if somebody is interested. Thank you.
Thanks a lot, Rajendra, for this wonderful talk. And if there are some questions, I think Indranil wanted to ask a question.
Yes, that's right. So I wanted to ask, how exactly is the oh, can you go back one slide to where you were showing that only G by C cubed is constrained? So one thing I wanted to ask, how exactly is capital G supposed to vary in your model with the time?
It is supposed to vary as G supposed to vary as F cubed.
And how is F supposed to vary with cosmic time?
F is supposed to vary in cosmic time.
Or with the scale factor?
With the, yeah, just a second, let me get back to that. Here, F is supposed to vary. I have assumed this function, but it doesn't have to be this function. It could be anything. But this is the function which I found is easy to handle.
Okay, but so T minus T0, and what is the time scale of this alpha parameter? Because alpha is inverse time scale, obviously.
Alpha is a constant.
Yeah, but how much is it?
How much is it? Oh, yeah, it comes to, see, alpha comes to about point, in this case, come to minus 0.8 times H0, you might say.
Oh, so alpha is 1.25 Hubble times.
That's right.
Okay. So, right, I see. So basically F is supposed to, okay.
But it's a minus. It has a minus sign.
Okay, so
because when I write in these equations here, just try to see this one here. See, this is the H plus alpha square. This is what it is. So it is minus sign here. So
that means like F is dropping with time.
Yes.
And therefore capital G is dropping with time.
That's right.
Okay, so what I wanted to ask, so there's obviously observations don't just constrain like G over C cubed. There's constraints only on the value of G. One of the things that I was wondering about, so the luminosity of a star like the sun is proportional to G to the power of 7. There was a paper by Teller, 1948, which showed.
I'm familiar with that.
So if that is the case, then obviously with higher values of G in the past, the stars would all have been like, the luminosity would all have been much higher. And
no, but you have to consider the full expression there, not just G to the power 7, because there are G involved in there. There is the Boltzmann constant involved. There's the Planck constant involved. All these things have to be seen in this equation and then find out what it is. I have tried to study it. Actually, I published one paper earlier on that subject. And in fact, that paper was based on earlier concept which I had, which the cancellation was not complete. But there is a cancellation which happens, which leads to the effect is not as severe as you are saying G to the power 7.
Right, because there's changes in, for example, the speed of light as well. And
yes,
the Boltzmann
speed of light is there. All these parameters are there. We have to consider all of them. And that's what I try to show in here, that, you know, for example, this period, orbital period in this case, is, that's what they measured when they are doing a lunar laser ranging, for example. That's when they measure that period. Then they are trying to say, okay, if this period varies, it doesn't vary, so G doesn't vary. But G and R cube variation are canceling, because R also varies because it is measured in the speed of light. And
Well, R is measured as like a time multiplied by the speed of light. So if the speed of light changes, then...
Yeah, that's right. So that will change. So that cancels. Similarly, the gravitational lensing, we had geometrical and Shapiro effects. We take that into account. Then we find there is the G over C cube involved. So that also cancels. I have yet to come out with an experiment which will show that it can be measured.
So, okay.
Sorry to interrupt, but we're really running out of time. So sorry, I think if Jenny and Luis also wanted to comment something.
Yeah.
Yes, I mean, I just have I think it's important because this is highly interesting and is one of the few models that I have seen that it's actually tested with a lot of different data. So I was wondering, a lot of the data that are out there in public, they are usually calibrated by ΛCDM. So I was wondering, which difficulties did you encounter to test your really unconventional model on the data that is out there, which might have some ΛCDM in this through the back door?
I have yet to find something. Yes, you are right that if you consider the CMB data, we are working on it. We have not tested on that completely. We have just Sound Horizon and BAO. That's what we have done. But and similarly our early the element genesis, for example, we have not been done it yet, but we are working because all these things take time and resources, and we have limited resources. But yes, this is very important. But in terms of the variation of the constant itself, there a lot of work has been done, but that has been done on constraining one constant only, not considering the variation of others. But when you consider all the equations, I have done myself a lot of work on that and published it. But really, we find that when we have this kind of cancellation effect, when we are trying to see the measurement variation of f, dimensionless constant f, which we have presented, that's what we have to see rather than anything else.
Thank you.
So, Luis, if you want to make like a quick question or comment?
It's a very good question. Yeah, I appreciate that you work on a theory that includes tired light, of course. My question is, since there are about over 100 different theories of tired light, and they don't all make the same predictions, which one did you use?
Actually, a tired light theory which we have used is the simplest one. This is let me try to show you what it is. That is this. We have just the proper distance defined by this.
Okay. And the other distances are just multiplied by various factors of square root of 1 plus z. And yeah, okay. It's like okay, thank you. Yeah.
Okay.
Okay, so thanks again, Rajdra, for this great talk. And if there are no more questions, we should move to our next speaker, which is Nick Samaras from Charles University in Prague. And he's going to be talking today about the initial conditions of the new HCM model. So, Nick, whenever you want.
Yeah. Hi, Helena.
Hi, Nick.
So, can you see that?
Yep.
Okay, can you see my cursor?
We can see your cursor, yes.
Okay, that's good. So I'm going to talk about the initial conditions of the NUHCM and a little bit about the NUHCM in general. So I'm a PhD student at the Astronomical Institute of Charles University in Czech Republic. Yeah, so the initial motivation for this cosmological model comes from like all the studies by Bob Sanders, who has plotted here on the y-axis, you can see the Newtonian dynamical mass with respect to the observed mass. And he observed that there is a discrepancy between the Newtonian prediction, and when he did the same exercise, but now plotting the Mondian dynamical mass, then there is still some kind of discrepancy for some clusters, and he was trying to attribute this discrepancy to some phenomena. This is a follow-up study, well, I think last month by Benoît Famé on galaxy clusters, which this study is reporting this missing mass when you're trying to plot the Mondian mass. This is high redshift galaxy clusters. So this NUHCM cosmological model is consisted of basically two things. That's the Mondian gravity and a sterile neutrino. So why? Because we want to keep the successes of Mond on the galaxy scales, like the baryonic-Tuni-Fisher relation or the Faber-Jackson relation or the RRR. And the neutrino, which is still hypothetical, it's not detected. It's sterile, so it interacts only via electroweak forces, and it is supposed to be around 11 eV. And it's the free streaming length of it, it's going to be around 3.5 megaparsec, which is around the size of the diameter of a galaxy cluster. So this it's going to make the neutrino contributed on clusters, and it doesn't cluster, it doesn't group together on galaxy scales, because then you have Mond. But in this case, with this free streaming length, it doesn't affect the CMB as well. So again, a little bit about the history. As I said before, Sander has, after having made these observations and these studies, he has postulated that there might be neutrino contribution, which initially he postulated in around 300 eV. And then later, Angus in 2009 had actually taken, and he has taken the WMAP data, and he replaced the cold dark matter contribution to the neutrino contribution. Well, the rest of the parameters, they stayed more or less the same. And he actually managed to fit the WMAP CMB fit. So after that, Katz et al. At 2013 they had made some studies with hydro simulations with early Planck data, and only last year, Wittenberg and our group, we have done the first hydrodynamical structure formation simulations using the latest Planck data. So, and last month I have submitted my last paper with my collaborators and with my supervisor, and this I'm going to show you in the following. So basically, what is this model about? Again, we keep the omega baryon the same, so all the contribution from baryons is identical to the lambda CDM. So in blue, you can see the standard lambda CDM values from Planck. And as you can see, this is the baryons stay the same. The cold dark matter now, it's eliminated, and all the contribution now went to the neutrino. So, however, the omega matter stayed the same, and consequently, of course, the omega lambda stayed the same. And we used the factor values from the Planck. And as you can see, we have fitted the Planck data. That's the Planck data here, what we call lambda CDM. We have fitted fairly well. And this was the initial conditions for the simulations. So what did these simulations show is that you can see at the right panel, on the first row, you can see the baryonic distribution, and on the lower panel, you see the baryons. At the left column, you can see these are smaller boxes of 200 megaparsec over H box. And at the right, you have a bigger box, so you zoom out more if you want. These are 400 megaparsec. And you can see that you have galaxy clusters forming across cosmic filaments. You have big voids. And you can actually see that at the bigger boxes, there is convergence to homogeneity and isotropy. So wherever the observer stands, he sees basically the same thing. Of course, furthermore, one can notice is that the neutrinos follow the baryons. So as I say that you don't see any neutrino isolated in the void. So all of them cluster together where more or less the baryons are. However, what we have, when you do a further analysis of the simulations, one can see that all these structures, filaments, first galaxies, they form very late with respect to the latest James Webb Space Telescope observations. So you can, in our simulations, which is of course subject to resolution, the structures that they were forming were around Redshift 4, while this is this is intention with James Webb. And we have too many massive clusters and too many low mass clusters. So one note before I go to my next slide is that this is also observed in ΛCDM simulations. In the past, I have some backup slides to show you. So they have done basically the same thing. They have assumed all the dark matter, all the missing mass contributed by neutrinos, but instead of Mondian gravity that we have, they do that with Newtonian gravity. And they also report that they have too many rich clusters, basically. So, and here is the Mont cluster mass function. This is at Redshift 1 and this is at Redshift 0. And as one can see, this is for El Gordo cluster, the mass of huge massive galaxy cluster at Redshift 0.87, I think. And we have actually massive clusters bigger than that, more massive than El Gordo. And this, of course, due to the accretion of mass at lower at the Redshift 0, you can see these gigantic objects at 10 to the 17. Again, now what we have done, I have also awarded the grant. I spent 3 months at the University of Innsbruck in Austria through a collaboration grant between Czech Republic and Austria. And what we have done, firstly, is that we calculated the likelihood of the models. So as a technical note, we have used the Cosmology package, and with the test sampler using Bayesian statistics, one can basically see how confident, how the likelihood of the models. So the closer these values go to 0, the more confident the model is. And one can see that ΛCDM fits the data very well. And the initial NUHCM parameters, they have low confidence to the model. So the next step was to basically do some Monte Carlo Markov chain simulations, and using this sampler again with the same package, we have imposed some priors to the 6 free parameters of our model. The first one is, of course, the neutrino, because that's the most crucial parameter of the mass of the neutrino, the energy density of it. Then it's the Hubble constant. This is the tau is the optical depth at the reionization era. That's the spectral index of the for related to inflation, and that's the AS, which is this gives the amplitude of the scalar modes of the perturbations. And last, this is the A Planck, which was calibrated due to Planck observations. Basically, this depends on the observations. Once again, the omega baryon stayed the same, and the omega CDM was eliminated. So using these priors, we tried to fit the CMB, and this is my beautiful result. Yeah, so you can see that you have the Planck data with the blue points and the error bars. The dotted or dust, maybe red line is the camp. This is the initial conditions that we have used for the simulations. And as you can see, although the pattern is quite good, I mean, the peaks are offset, and the fit with the parameters with Cosmology is the green line. And as one can see, basically the fit is, almost perfect, except of these large scales. which probably depend on the well, not probably, they depend on the gravitational potential and the clustering. So this is probably depending on the well, of the CMB lensing, which is not fully developed on MOND yet. So yeah, so the resulting parameters of the fit now they're very surprising. Well, the omega nu was increased a little bit. It was again, the blue values are from the lambda CDM, which is the standard ones, and the black one is the values from the posterior. So the omega nu was increased by 10% from 11.12 around 0.13 now. The fit was giving a very low H0. So once again, reminding that the first guesses for the Hubble constant was around 50, between 50 and 100, and I put the value back to its origins. The tau also is increased. The spectral index also. The AS was decreased as well. This is connected to the relativistic degrees of freedom from the neutrinos. So this was also expected to change, to deviate significantly. The A Planck stayed the same. And then, of course, since you have they are degenerate, there is a degeneracy between the H0 and the omega matter. So this is very low. The omega matter now becomes significant, and it gives around 0.5, 0.495. So it's a highly matter-dominated universe, and consequently, the omega lambda decreased also significantly compared to lambda CDM. So this was an important result. And as I said, this was submitted to MNRS. And the next calculation, since I had the H0, then the next question is, of course, to calculate the age of the universe. And I used the equation from the Hasselbauer et al. Paper about the KBC void. Indra is talking about that. So using this formula, the result is around 19 gigayears. So it's a very old universe compared to lambda CDM. So there are some objections to that, because this might lead to early exclusion of the model, but I have also some backup slides if one has a question to this. So yeah, the next thing to look at was the power spectrum, and this is the power spectrum at Redshift 199. I've plotted that because this was also at the paper of Wittenberg et al. We have plotted again the power spectrum initially. Initially means at the beginning of the simulations. So this is a log-log plot, and then one can see that at the lower k, so that means large scales, you have all the models agree will have approximately the same power, but as one goes to lower and lower scales, so bigger k, the lambda CDM has more power because of the contribution of basically of the cold dark matter around the galaxies. So you have these probably NFW halos, while the contribution of the neutrinos, they are similar for these models, but the contribution basically is basically very small. So you don't they don't cluster, neutrinos don't cluster at the galaxy scale. So this was expected by the theory. So next is the transfer function. Another significant result. Again, this is, so just to explain, there is a transfer function for all the species. So there is a transfer function for baryons, for CDM, for neutrinos, for the transfer function of all these species together. So I'm plotting now the CDM, so the transfer function of the cold dark matter of the lambda CDM. So it basically stays more or less the same in all the scales of this range. So this is around the galaxy clusters and galaxy scales. So this clustering scale that we are actually interested in. So the red line is again from the Wittenberg et al. Paper. And And yeah, so you can see that neutrinos cluster on these scales. You have these oscillations. But the green line now, because the neutrino contribution becomes bigger, this excess of power between the green line and the red line might actually be important for the new set of simulations because this might affect the distribution of the cosmic structure, and we might not get finally these too many massive or too many low mass clusters in our simulations. So this is a motivation basically for more work. So yeah, apart from that, well, I have some formulas for the cosmological distances. I'm not gonna now go into the formulas. I don't have this time. So I've plotted the distant modulus, well, the classic plot with the Pandion and Suess data, and all the models are basically indistinguishable, so they predict basically the same distances. But however, when one plots the DM and the RD is the distant ladder, the distant ladder is model dependent. I can show you once again whether the distant ladder is coming from here, and that's the Hubble parameter, which is model dependent. So the blue line is the lambda CDM values. The points are, of course, also model dependent. They're coming from DESI. The red line is the original Wittenberg et al. Paper from the NUHCM. And this model is over predicting the DM distances, as one can see. But when you do the same exercise with the DV, then you can see that basically none of the models predict the distances very well, especially at higher redshifts. But then one note is that again, this I don't know how these data points are constructed, so probably one needs to take a note on that. Like maybe these are model dependent. So yeah, that's basically it. So my conclusion is that one can make actually a model with MOND, but with a small hot dark matter component only on the galaxies, on the cluster scale. So we win with MOND. This you don't need any. You only have the modified gravity on the galaxies. The sterile neutrino is better motivated with respect to hypothetical cold dark matter because of the neutrino oscillations, because we know that when the neutrino oscillate, they change their masses, and this might give a sterile neutrino, which is non-active. Again, this model is suffering from late galaxy formation. I have made the model, the final one, much more confident now with the Planck data, but however, this gives a very old universe. Nevertheless, there are some observational studies that report that the universe might be older than the predicted lambda CDM value of 13.8. And last one is that I have also awarded some CPU hours to do supercomputing simulations with the OPT and the NUHCM initial model as well. So yeah, that's it. Thank you.
Thanks a lot, Nick, for the talk. It was very interesting. So if there are any questions. So Indranil wants to say something.
Yeah, I wanted to comment on the another constraint on cosmological models, which is from the turnover scale in the matter power spectrum, which essentially tells you the size of the cosmological horizon, not the sound horizon, but the cosmological horizon at the epoch of matter radiation equality. Now, this was constrained by Philcox et al. 2022. And what they got is omega m of 0.338 and little h of 0.648. So they basically were able to constrain the product of the two as very close to 0.22. This is omega m times h naught in units of 100 kilometers a second, a megaparsec. Now, can you show the cosmological parameters that you get in your new HDM case? Okay, so in here, if you were to multiply the omega m of 0.495 by the little h of 0.5564, then you would get 0.275. So that is obviously 25% more than what Philcox et al. But their uncertainty was only about 3%. So have you thought about the constraint from the turnover scale in the matter power spectrum and how that might affect your model?
Yeah, and we have discussed that again. I didn't have time to think about that, but yeah, it's I know about the Philcox constraints because we have worked on that as well together.
Yes.
So yeah, I might have a look at that. Yeah, after these talks. Yeah, but
Okay.
that's very interesting. Yeah.
Thanks. Just let people ask other questions.
I think Pavel also wanted to comment something. Pavel, did you want to say anything?
Yeah.
But who?
Pavel, I thought you had your hand raised.
Yes, I did not hear.
Sorry, maybe my audio is not very good.
So, Nick, a very nice talk. Thank you. And just one little comment at the end. In the conclusions, you mentioned lambda CDM predicted the age, right? And it, of course, did not. It's just
there is a prediction. Might be wrong, but there is a prediction.
No, there's no prediction. It's a fit to the CMB.
It's basically it's basically this.
It's exactly as you're doing. So your fit is no better or worse than theirs, but it's just one has to. And this is like a general note to the community. Whenever a lambda CDM is involved, people all too quickly use the word predict.
No, but in this case, Pavel, lambda CDM does predict it because the parameters are calibrated using the CMB without any knowledge of the actual age.
It's a fit, and it's the same like here. It's fitting to
it's
the
a
data.
Prediction.
And no, it's not. The prediction would be
to the data, and then it's predicted.
A new phenomenon which you have not, for which you did not have any data. This age is derived from the data.
No, it's derived from the data on the CMB, but that's not related.
It's from the data, exactly. Yeah.
Yeah, but that's not related to the age of the universe.
If
the
you
CMB.
wouldn't have the CMB, you wouldn't have the age of the universe.
Of course. Well, okay, it's calibrated on. That's like saying Newton.
It's not calibrated. It's fitted. It's a fit. It's a fit to the data.
Well, okay, it's not calculated from first principles. It's like saying Newton was able to predict the motion of the moon by doing terrestrial experiments to work out like the value of capital G and the mass of the Earth. So you have to have some observation.
No, it's not. I mean, the age is one of the parameters which one fits to the data.
No, that's not true.
It's like predicting the position of a planet in the future where you haven't observed it yet.
Okay. So right. In that sense, yes, because when the CMB observations were collected, the age of the universe was known reasonably well. In that sense, you could argue that it's not a prediction. But certainly the actual age of the universe, as measured from the old stars and globular clusters, is not used to constrain the lambda CDM cosmological.
It's obtained from the CMB.
It's obtained from the CMB.
Yeah, exactly. Yeah, and maybe you can argue from the supernova 1A. No? So I'm just arguing, saying, be careful with the word predict, and also with merger. Just like that.
Yes.
But cut it out of your vocabulary. Just use these words in the context of cosmology.
I didn't even realize that one. Okay.
Yeah, I know. Okay.
Okay, so I think we have to move now to our next speaker, which is Tiziano Schiavone from the University of Galileo Galilei Institute for Theoretical Physics. And the title of his talk is An Effective Hubble Constant in FR Modified Gravity in the Jordan Frame. So, Tiziano, whenever you would like to start, the floor is yours.
Thank you. Hello.
Hi.
Can you see my screen?
I can see your screen, yes.
Okay. Now in full screen mode. Okay. Okay, I'm Tiziano Schiavone, a postdoc researcher at the Galileo Institute in Florence. First of all, I would like to thank the organizer for this opportunity. In this talk, I will discuss modified gravity theories as alternative extensions of general relativity to explain not only the present cosmic acceleration, but also investigate the Hubble tension. I will briefly introduce the standard cosmological models and the Hubble tension, one of the most serious open problems in cosmology. I will talk about the possibility to use measurements of the present expansion rate of the universe, the Hubble constant, as a diagnostic tool to test cosmological models. Then, starting from the analysis in redshift beams of the Panton sample of supernovae 1A, I will show you the results pointing out a decreasing trend of H0 with the redshift. I will present a theoretical interpretation of this evolution in F of R modified gravity theories, introducing an effective Hubble constant that evolves with redshift. This presentation is based on these 3 published papers in collaboration with a team of cosmologists. The project started during my PhD at the University of Pisa. Okay, let me start. One of the most challenging problems of the ΛCDM model is the Hubble tension. As you know, the H0, the present cosmic expansion rate, is nothing more than the Hubble function H evaluated today at redshift Z equals 0. So H0 is a constant by definition, obviously. However, as presented by, in this plot by Di Valentino et al. 2021, measurements of H0 from the early universe are incompatible with those based on local probes at low redshifts. You can see here this pink band and the blue band. And this 5 sigma discrepancy could be due to systematics in supernovae and or CMB data, or it could be a signal of new physics. Very briefly, once you specify GR and the content of the universe, you can focus on the cosmic expansion with the Hubble function. Here you can see the expression of the function E of Z for a flat ΛCDM model in the late universe with a cold dark matter component and a cosmological constant lambda. Other extended dark energy models included an equation of state parameter different from -1 that evolves with the redshift Z, like in the W0 WACDM model, following the CPL parametrization here. But an interesting and original perspective to test cosmological models is to use H0 as a diagnostic tool. You can see here on the top, this ratio must be a constant, where H of Z can be obtained in principle from observational data, cosmic chronometer, or baryonic acoustic oscillations, while the function E of Z here in red incorporates the considered theoretical model. The same procedure can be applied to the relation of the luminosity distance, and this ratio again must be constant and equal to H0. So in this way, observational data from probes at various redshift can be useful to test these ratios. Incompatible values of H0 or an evolution with Z may indicate a mismatch between observational data and the cosmological model considered. In other words, if we force data analysis to conform to the prescribed ΛCDM model and still observe discrepancies, then H0 effectively may acquire a redshift dependence, as explained also by Krishnan et al. In 2021. So now, considering this perspective, we focused on the Panton sample of supernovae 1A in this redshift range from 0.01 to 2.26. Bearing in mind the Hubble tension, we wondered if the tension persists also within the Panton sample redshift range. And this was the starting point of our redshift B-net analysis. The basic idea is very simple. We divided the Pantheon into equally populated subsamples in different bins to check whether the values of H0 are constant. Finally, we extracted the values of H0 from each bin after a statistical analysis, and these are our results for a flat ΛCDM model. H0 seems to exhibit an unexpected decreasing trend with redshift, regardless of the number of bins. We used also a nonlinear fitting function H0 of Z with this red curve, where H0 tilde and alpha are fitting parameters. But is it a fast and clear evolution of H0? The alpha parameter for different bins is approximately 10 to -2 and is consistent with 0, namely no evolution, in roughly 2 sigmas. So it is a weak evolution. However, as you can see in these fitting parameters in this table, the alphas are compatible with each other for different bins. So we we have this slight unexpected evolution of H naught of Z. But if the observed trend is not related to a specific probe, the Pantheon sample, but is intrinsically due to some redshift evolution, one may ask what happens in the early universe at very high redshifts. In other words, is there any way to adjust to bridge the gap solving the H naught tension and linking low and high redshift measurements? So we extrapolated the fitting function H naught of Z to the redshift of the last scattering surface, Z1100, and our extrapolated values are compatible in 1 sigma with those inferred from the Planck measurements for the CMB. Therefore, H naught may evolve with the redshift matching measurement obtained from different probes. For completeness, here I report other evidence of unexpected decreasing trends of H naught from the independent analysis of combining different datasets. Now, what are some of the possible reasons for this trend? H naught must be a constant by definition, so its observed evolution could indicate an incorrect picture of our universe. H naught of Z could be due to astrophysical factors, such as the evolution of a supernova parameter not considered so far, the stretch parameter, or it could be related to the calibration of Cepheids and supernovae in the sample. Alternatively, if it is not due to statistical fluctuations or systematics, it may signal a new cosmological paradigm. And in the following, I will focus on alternative scenarios different from GR. So the Hubble constant tension, the need for ad hoc dark components whose exact nature is still unknown, may signal the breakdown of GR at cosmological scales and motivate the search for an extension. For those unfamiliar with F of R modified gravity theories, the gravitational Lagrangian density is replaced by a function of the Ricci scalar, F of R, an extra scalar degree of freedom compared to GR, useful for solving open problems. For instance, a geometrical modification of GR may mimic a dark energy component. It is often convenient to reformulate F of R gravity in the scalar tensor representation in the Jordan frame, using a dynamically equivalent gravitational action. The extra degree of freedom given by the F of R is converted into a non-minimally coupled scalar field phi. And this extended theory of gravity provided different cosmological dynamics compared to GR, with a modified Friedmann equation, a modified acceleration equation, and a scalar field equation. Now, we look back to the trend of H naught of Z. It's important to stress that we obtain a similar trend from analysis also in redshift bins, both in the W0 ΛCDM model and the Husa-Wiki F of R model, one of the most studied F of R model, which provide an alternative to the dark energy component. In other words, this trend didn't disappear also in the analysis with these models. So we need to build a new theoretical model, not only to mimic a dark energy component, but also to provide a mechanism for an effective Hubble constant that evolves with redshift, which is not accounted in the lambda CDM model, of course. The main goal is to match independent measurements of H naught from the CMB and local probes through a running Hubble constant. So to this end, let me move to the main part of this talk. F over gravity in the Jordan frame look promising since an effective Newton constant is redefined and related to the scalar field due to the non-minimally coupling between the metric and the scalar field. And this fact affects the cosmological dynamics, leading also to a redefinition of H naught. Let me show you. We rearrange the modified Friedmann equation in terms of the redshift. This is the modified Friedmann equation in the Jordan frame, and we rewrite the potential as a cosmological constant term plus a small deviation. Now, neglecting this latter term, G of phi, we end up with a Hubble function that it is quite similar to the one in the lambda CDM model, but now with an effective Hubble constant that evolves with the redshift. You can see that the non-minimally coupled scalar field plays a crucial role. In other words, we move this extra degree of freedom in the Jordan frame of F over gravity to redefine an effective Hubble constant that evolves with the redshift. Furthermore, solving the cosmological dynamics in the Jordan frame, we reconstruct analytically the expression of the scalar field potential and compare it with the numerical solution. We used these initial conditions also to reconcile late and early time measurements of H0, and this is our result. On the left panel, you can see the potential terms in terms of the redshift, while on the right in terms of the scalar field, which follows a power law. Here also the effective Hubble constant decreasing with this function. You can see also that the numerical and analytical solutions are plotted in red and blue line respectively, and they are in good agreement for low redshifts in the dark energy dominated universe, in the regime in which our initial hypothesis for the potential is valid. Also note the occurrence of a flat region in the potential profile at very low redshifts, a scalar field in a near frozen dynamics. And you can, this can be appreciated if we compare different contributions in the modified Friedmann equation in this plot. The black solid line is referred to the matter component, the standard like in the ΛCDM model, while a cosmological constant is reported in brown here. Now, the potential term with the blue line and the numerical solution with the red line can be regarded as a very slowly varying cosmological constant. It is very close to the cosmological constant term in ΛCDM. Furthermore, this potential in the Jordan frame of F over gravity also provides a decreasing trend of the effective Hubble constant. Here, the resulting effective Hubble constant incorporates an extra degree of freedom given by the scalar field dynamics. I reported here again this relation. This is not the Hubble constant like in the ΛCDM model. And here you can see its evolution with the redshift Z, and this evolution could be measured in principle at different redshift considering different cosmological probes. Finally, expanding our analytical solutions for low redshifts, we can calculate the form of the F over function associated with the potential profile in the Jordan frame. So we found, basically, using these relations in the Jordan frame that connect the potential and the functional form F of R, we found the form of the F of R function in the well-known quadratic gravity, with a quadratic correction in the Ricci scalar. I would like to stress that this is an approximated solution valid only for low redshifts, given by this expansion. Moreover, it can be shown that ΛCDM is recovered as alpha approaches 0. So this parameter alpha, in addition to being the physical parameter that describes the evolution of an effective Hubble constant, also denotes small deviations from GR. And this alpha was the same parameter used in the analysis of the Panton sample here. Yes, this is in the fitting function. So let me summarize. In conclusion, we have provided a new interpretation of the tension with an effective Hubble constant. It may no longer be a discrepancy between independent measurements of H0, but an intrinsic evolutionary behavior in an extended modified gravity scenario. And here we will focus on we focused on the F of R modified gravity proposal. However, we need better constraints on the evolutionary parameter alpha with other probes. And in the future, so we will try to also to include other data sets in our analysis to test an effective Hubble constant via Monte Carlo method. And now I'm working also in an incoming paper with effective cosmological parameters in F of R and T gravity to address H0 and sigma 8 tension simultaneously. And these scenario are modified gravity scenario considered as an extension of F of R gravity. And this procedure can be generalized for a plethora of models that predicts deviations from ΛCDM, and additional degrees of freedom can be restated in terms of an effective Hubble constant that evolves with redshift. This this procedure is another indication that, as also reported by Stanley Magnozzi in this paper 7 inch, that early time new physics alone is not sufficient to solve the Albon tension. This effective Hubble constant procedure can be considered as an indication that we need to explore also late time modifications of lambda CDM model. And thank you for your attention. I'll be happy to answer your question or discuss further.
Thanks a lot, Tiziano, for this very nice and interesting talk. And yeah, if anyone has any questions, please go ahead. Indranil has a question.
Yes, so I wanted to ask about, so I guess your H naught f of z is basically the statement that the E of z curve is different to the one in the Planck cosmology, right? Because that must be the essentially how this is working, right? So my question was, have you tried looking at the BAO data? Because that gives like a tight constraint that the EFZ does look like the lambda CDM shape.
Yes.
Yeah.
Thank you, Indranil, for your question. Yes, actually, I didn't mention for the lack of time, but yes, we extended this analysis, including BAO data in the second paper here, published on Galaxies. This we combined the supernova 1A Panton sample with the baronic acoustic oscillations, and we added one BAO in each redshift bin, and the results are quite similar. I only mentioned here on this slide about this failure. Yes, about this. I'm sorry, this decreasing trend of H naught from bin-head analysis, also including BAOs. But in this kind of analysis, we use two free parameters, H naught and omega matter 0, in lambda CDM.
Yeah.
And use the MCM analysis, but again, we obtain this. I have maybe in the backup slides some plots and also the fitting parameters. Yes, this is the bin analysis with BAO, but again, we obtained, yes, these alpha parameters, which is consistent with 0 in here in 1.2 sigma, in 3 bins. Yes, it's still a weak evidence, of course, of an effective Hubble constant, but also including BAOs, which is consistent, which are consistent with the Planck data. Of course, also the BAOs are usually studied and analyzed within the lambda CDM model.
But they're purely geometric probes, so one doesn't have to do that, right?
I'm sorry, could you repeat?
They're purely geometric probes, though, so one doesn't have to assume lambda CDM.
Ah, yes, you are right. If you consider only the deformation of this, yes, of this object from a geometrical point of view, yes, you can also use other cosmological models.
Okay.
Okay, I think Nick also had a question.
Yeah. Hi, Tiziano.
Hello.
Can you show this plot of the age of Z with respect to Z? I think so. Yeah. So yeah, okay. Have you extended that to lower and lower redshifts or not? This is because of the bin of the data.
You mean a very low redshifts?
Yeah.
Yes. Our yes, the Panton sample is consists in this data.
It's restricted up to 2.5, I think. Yeah.
Yes, you're right. But of course, we are where is it? I can show you the right. Okay, this is the redshift range of the Panton sample. But to do a proper to perform a proper statistical analysis and having constraining power, we need to include many supernovae in each redshift bin. So we decided to use these redshift bins between these in these redshifts. Of course, supernovae are more dense are very low redshifts. But it could be interesting to investigate, as you mentioned, these redshift bins are very low redshifts also, to include other effects like deviations from the cosmological principle, cosmic voids. Here we didn't include these effects, but it could be very interesting because it could be probably a local effects.
Okay, good. Thanks.
Thank you for your question. Yes, here I only mentioned these cosmic voids and
Okay, so if there are no more questions, I think we can thank again our speaker and also all the speakers in this contributed talks section. And we can move now to the last section, which is the poster one. And we have our speaker, Luis Marmet, who is going to be talking about diffuse light-electron interaction, special redshift effects in astrophysics. So, Luis, whenever you want, you can start sharing.
Thank you. Let me see here. Oh, someone else is still sharing.
Sorry, I have to.
Tiziano, yeah. I'm going to wait till you're. Ah, perfect. So, so thank you for having me. You should see my slides now. And thank you for giving me the last word as well. I had prepared a talk with a bunch of equations, and I thought since I only have 5 minutes and it would take me 2 minutes to explain each of these equations, I would already be out of time. So instead, I decided for the last presentation to have it a bit on the lighter side and tell you a story as an analogy that you can take home. And so my story is based on an old event, fire that happened 200 years ago. And I want to draw your attention to these people here at the lower left corner. They're carrying buckets of water in order to try to bring as much water as possible to extinguish the fire. So this is called usually a bucket brigade, and this was found to be an efficient way to move water. So in my analogy, I describe a beam of light, a light beam propagating toward the right as a bucket brigade. I call it the Maxwell-Dirac photon bucket brigade. And in this analogy, the buckets are photons. They move past the electrons, these men here, of course, at the speed of light. We're talking about a light beam. The water in the bucket represents the energy of the photon. And of course, not a drop of water is lost. You start with a blue bucket at the beginning. You end up with a blue bucket at the end. Now, let me turn this off. Nice. This, of course, describes, this is compatible with Maxwell's theory of wave for light, and also describes Dirac's quantization of light. Now, to make the story more interesting, I had another beam propagating in the opposite direction toward the left, with buckets that have a slightly longer wavelength, so they're green. Of course, this is also compatible with known physics. So the story starts when one of these electrons here gets very thirsty, they're working very hard, and decides to remove a bit of energy from the bucket, which turns it green, of course. But then immediately he thinks, well, there's a problem here because now I'm sending green buckets down the line. And of course, Maxwell will see this lower frequency of his radiation and think, oh, there's a problem here. Same for Dirac. They will both think, oh, our equations are not valid anymore. So this electron here realizes it's making a big mistake. However, there's a solution, and it's very simple. The electron thinks, well, I can use this interaction here, described by this formalism, and simply send the bucket to the other line where there's already green buckets. By doing that, only the blue buckets will end up on this beam, and so Maxwell and Dirac will both be satisfied. And additionally, Einstein will also be very happy because this is a demonstration of stimulated emission where you insert a new photon in a beam and it has the same color and the same direction as the original photons in the beam. So this trick here is actually very good. The photon is satisfied and all the known laws of physics are satisfied. Now, usually light we see are not single colored, monochromatic. It's not only blue or green, there's a full spectrum. So to make the story more complete, I show you what happens here with various colors for the buckets and many beams propagating in opposite directions. Now this is a bit overwhelming, but I want to draw your attention to this one here, this green beam, which starts with many buckets traveling across. But because of the tendency to shift buckets to the other line, slowly the rate disappears. And by the time you reach the end here, there are almost no green buckets left that are traveling down this beam. Now, if you look 2 beams above, all these buckets that are being transferred, you see that the yellow beam is increasing in intensity. And actually, by the time you reach the end, there are lots of buckets here. The beam is very intense. So this is the end of the story. You just have successfully shown that you can change intensity of light beams just by using this simple interaction. And this is actually described by the first equation I had on my slide. Now, what does this mean to astrophysics? So I'm going to simplify a bit this thing. And I've eliminated the beams moving to the left. So this is a spectrum, actually, of the JADES Z14 galaxy, which shows the Lyman break. And as you can see, the blue wavelengths are very low intensity, so there are not many buckets traveling. Just below Lyman alpha, you have a very high intensity, which is represented by the green buckets, lower intensity in the yellow, and so on. Now, as this travels through the electrons of intergalactic space, the intensity of the green beam decreases to almost nothing. The intensity of the yellow has increased, and orange and yellow and red have increased as well. So as a result, you get the same spectrum, but it appears shifted in wavelength toward the longer wavelength. And so what has been achieved by all these interactions with electrons here is a spectral redshift. And additionally, the energy that's been taken out from these photons is now in the form of heat. So I've represented the red dots here, which are electrons that are heated by the process. So this is an observer here who's very happy to see Lyman alpha radiation at yellow wavelengths. So this is the end of the story. That's what I'd like you to take home. So I'm going to conclude. There are, as I mentioned in my question, there are over 100 tired light models that all claim this tired light model explains redshift. So I don't expect anybody to stop what they're doing and start working on what the model I've just presented. But in revenge, 100 years of variations on the theme of modified relativistic gravitational space-time distortion has produced a cosmology that's dominated by dark sector and which still has significant tensions. And so this is not convincing me that tired light is actually not present in space. So the second message I'd like you to take home is that redshift is the common element to everything in cosmology. Every measurement we make is dependent on redshift. And different tired light mechanisms don't all make the same predictions. And so I think that the new redshift interpretation should be examined very seriously. With that, I'll end. Thank you very much.
Thanks a lot, Luis, for this very illustrative explanation of. I mean, I thought it was very, very nicely explained. And yeah, if anyone has questions. So Lior has a question.
Yes.
Yeah, thank you. That was really fascinating. Thank you so much. My question is, can you think, for instance, of an experiment that we could do in a cosmological setting to test those wonderful things that you just said? Even theoretical experimenting.
It's very difficult. Of course, I've been trying to think about an experiment or many experiments. It's very difficult. The first difficulty is that most of the data, or all the data that's being collected, is analyzed in terms of an expanding universe. And so this has to be undone before we start analyzing the data, looking at it in terms of a tired light idea. And so, I mean, I don't have anything concrete because it would require a lot of work. And I mean, astronomy is not my specialty. I'm from the world of optics. So I've been reading about it and how data is analyzed. But now, this model predicts results that are similar to what is observed. And so it's difficult to say, well, sure, but ΛCDM does explain the data in the same way. And so which one predicts it more accurately becomes difficult to tell. Now, theoretically, there are things that can be calculated. For example, the strength of this interaction. If you know the strength, you calculate the strength of this interaction, and you know how many electrons are in the intergalactic space, then you can calculate what the Hubble constant would be just from first principles, right? And this I've done, and of course it works. So within the uncertainty of the number of density of electrons, you get the Hubble constant coming out of it. But specific calculations that would essentially distinguish between such a theory and another one, this is a little bit more complicated to think about. But I mean, I still have to do a numerical simulation because this thing is a bit complicated. What I've shown you here with all the wavelengths and buckets, this is a static solution. When there's a supernova, for example, then this is a dynamic solution. There's a delay because of the beams moving in the opposite directions. And so that's what stretches the light curves. But I don't have an analytical solution for that. I have to do a numerical simulation. And so I'm kind of in the process of checking all of this. And so, but perhaps once these simulations are written and I have the code, then I can think of experiments that should be able to be done.
Yeah, thank you.
Okay, so if there are no more questions or comments, I think we can thank again our speaker, and we can end the session on the conference here. So thanks a lot again to all of you who participated, either by giving talks or by commenting or by all of you who participated in any way and for being here. And also thank you to the organizers like Saddam and Alexia and Monsi and Indranil and of course Robert Monjo, who was the main organizer and who really put a lot of work in this conference and who unfortunately couldn't talk as much this conference because he was very sick. But also thanks a lot to all of you. And well, hopefully we'll see each other again, maybe in the next Challenges of Modern Cosmology conference. On the meantime, we also have a Discord channel. I think someone told me that there were some issues with invitation, but we will look into that and we will share the link with you in case you want to continue the discussion on Discord. And yeah, I guess I'll end here the recording and
thank you as well, Elena, for all your work with the conference as well.
Sure. And yes, see you all next time. And yeah, bye.
Recording stopped.